Hello, this is Aayushi Shah reporting from Britain in 1667.
Hello, this is Patel reporting from Britain in 1667.
Just in, mathematician Isaac Newton, along with his contemporary Gottfried Leibniz, have just made the discovery of the derivative known. Using information from older mathematicians that many of you probably have not heard of, such as Isaac Barrow, René Descartes, Pierre de Fermat, Blaise Pascal, and John Wallis, who discovered the derivative, Newton and Leibniz have simplified the derivative so common folk like us can grasp what they are. Here's a recent statement made by Newton himself. I had the hint of this method of fluxions from Fermat's way of drawing tangents, and by applying it to abstract equations, directly and invertedly, I made it general. Using this knowledge from previous mathematicians, Newton applied derivatives to theoretical physics, and Leibniz developed a proper notation to show how these derivatives can be used. What is a derivative? In calculus, a branch of complex mathematics also strongly supported and developed by Newton, the derivative is the slope that is calculated at a point on the line tangent to a curve. This slope is the rate of change with respect to a certain variable. An example for us common folk to understand is when a wheel on a carriage is on the ground, the measure of the slope of the ground at the point where the wheel touches the ground is the derivative of the wheel at that point with respect to time as the wheel is moving on the ground. The change in position of the wheel with respect to time can also be conveyed as the velocity of the wheel. Here is a mathematic example. This blue line is the line tangent to the curve at the point 1, 1. Its slope is the derivative of this function.
Derivatives help with finding the acceleration and velocity of particle, carriages, or anything else when you know or are given the position. The first derivative of position gives velocity, and the second derivative of position, or the derivative of velocity, gives us acceleration. The speed can be found by taking the absolute value of the velocity, which is the derivative. Related to carriages, derivatives help calculate distance. Derivatives help predict fluctuations in the shares market and in machine learning, and they are important to function optimization, a component of calculus. They also monitor temperature changes in physics and are the base to deriving numerous equations, though most of us common folk don't usually take a part of this.
There are many ways to find the derivative of a function depending on the structure of the function. These methods were also invented recently when Isaac Newton and Gottfried Wilhelm Leibniz were looking into other aspects of calculus. One of the most common ways is the power rule, which is typically used for quadratic functions. Power rule involves taking the exponent, multiplying it by the coefficient, the number in front of the x, and decreasing the exponent by 1. If the number is a constant, it goes away. As you can see here, the power rule, you multiply the exponent in the front by the constant of x and subtract 1 from the exponent.
Another method is product rule, which says the derivative of a product of two functions is the first function times its derivative of the second function added to the second function times the derivative of the first function. A method used to solve derivatives of more complex functions is a chain rule, which expresses the derivative of the composition of two differentiable functions f and g in terms of the derivatives of f and g. This is used when a differentiable function, or a function that has a derivative, contains another differentiable function, and you have to find its derivative. As you can see, g of x is enclosed by f of x. First, you take the derivative of f, which is f prime of x, and then you put g of x inside that, and then you multiply all of that by the derivative of g of x, which is g prime of x. The chain rule is also used with trigonometric functions such as sine, cosine, tangent, cotangent, secant, and cosecant. Many who understand mathematics, which is not a majority of us, will understand how trigonometry works with derivatives. We can remember what the chain rule works with by thinking of PTA, power, trigonometry, and angle. So what are trigonometric functions? This segment is targeted to all our mathematicians out there. Trigonometric functions are functions of an angle or of an abstract quantity used in trigonometry, including sine, cosine, tangent, cotangent, secant, and cosecant. All these trigonometric functions are differentiable. As you can see here, the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. The derivative of tangent x is secant squared x. The derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x tangent x, and the derivative of cosecant x is negative cosecant x cotangent x. These derivatives of trigonometric functions involve the mathematical process of determining the rate of change of trigonometric functions with respect to the variable angle. This variable angle is what the A in PTA stands for.
Although Newton and Leibniz both discovered the derivative, both mathematicians have different methods of displaying them. Newton's notation of the derivative consists of a y or an f with a dot on top, as you can see here, or here. This notation is often used in real-life applications of calculus, especially in physics, as Newton is also a physicist. Oftentimes, these derivatives are with respect to time. The Leibniz notation of the derivative consists of a dy over dx if the function is in terms of y, and a d over dx of f of x if the function is in terms of f. As you can see here, this is dy over dx, and this is d of f of x over dx, or dy over dx. This represents the change in the y variable with respect to the x variable, or the change in the function f with respect to x. Leibniz's notation is mainly used when dealing with integral calculus, differential equations, and multivariable calculus, all more complex components of calculus that many of us are unfamiliar with. We would like to formally thank Isaac Newton and Gottfried Wilhelm Leibniz for their mathematical efforts in allowing us common folk to properly understand the derivative in calculus and its many applications and components.
That's all for today on Wesley News Britain. Tune in again on a later time for more information on our country.